Hi, so we are looking here at modeling projectile motion, and the model for this projectile motion is right here. And I did a little bit of a visual where we have a cannon at an angle theta that fires a cannonball, which is that white ball that could kind of look like a snowball, that has a velocity that is tangent to its trajectory, where this dotted line is the trajectory. And we can decompose the velocity, which is a vector, into the y component and the x component. And those are all going to be functions of time. Now, if we just look at the ball, we can say, as we are shown on the left, that the forces, the overall forces in the x direction, we're applying Newton's second law, are equal to 0. And the overall forces in the y direction are equal to negative g times m, right? So the m here can even cancel. And all we have to do here is realize, hey, we're not modeling air resistance, so we're assuming there's no air resistance. Now they're saying to solve this with Laplace. So if we want to solve this system with Laplace, we would get m times what? Well, if we want to solve this with Laplace, we would get m times s. So here we're applying Laplace. S times big X of s, but I'm not going to write it. And this is going to be squared minus s times small x of 0 minus x prime of 0. All of that is equal to 0. And on the right-hand side, we'd get this same expression, but for the y. So this would be y prime of 0. And all of that has to be equal to negative g over s. Well, now that we have this, what can we do? Well, we can input the initial conditions. They told us that our initial conditions are x of 0, y of 0 are 0. So these are 0. And this, we found them. We said that the velocity, x prime of 0, is the velocity at time 0. Well, that is v naught cosine of theta. And for the same argument, this is v naught sine of theta. So we can rewrite this whole expression. And notice how the m here cancels out as well. So we get this whole expression, s squared times big X is equal to what? It's equal to v naught cosine of t. And if I divide by s squared, I get s squared here, and I freed my x. With the y, we're going to have v naught sine of theta minus g over s. So let me write g over s. And all of that, it has an s squared here, but if I divide by s squared, then I'm going to get s squared here and s to the third here. Now, if I apply the Laplace inverse to this, I recognize that I would get x of t is equal to, well, this v naught cosine of theta are just constants, so they're just going to be pulled out. V naught times the cosine of theta, and 1 over s squared, the Laplace inverse is just t. And for this one, I recognize that v naught times the sine of theta is going to be pulled out for the first term. And 1 over s squared, the Laplace inverse is t. Here, 1 over s to the third. Well, the Laplace inverse, now we need to do some manipulation, here we want to have a 2 factorial, but then we want to divide by a 2 factorial. But what is a 2 factorial? It's 2 times 1. So that's just 2. So now we can pull out the minus g over 2, and then here we'd have a t squared. And now we recognize that these are our kinematic equations. And we did part A, which was asking us to use the Laplace transform to solve the system. Now, for the solutions of the system in part A are parametric equations. By using x of t, eliminate the parameter t in y of t and show that the trajectory is parabolic. So what they mean for part B, they want us to solve for t using x of t. So I'm going to say x, and remember that x is always a function of t, but I'm just going to drop the t for readability purposes. And then I'm going to input this into the y. So y is now going to be v naught times the sine of theta times x over v naught times the cosine of theta minus g over 2 times x over v naught times the cosine of theta, and that's going to be squared, squared, squared. So what are we going to have here? Well, the v naught here cancels. I can rewrite sine of theta over cosine of theta as the tangent of theta. And so we really get this. Now we got v naught squared cosine squared of theta times x squared. And this is a parabola. This is a parabola. So our trajectory is parabolic as they requested us to show. Now let's go over to C. The results in part B, use them to show that the horizontal range of the projectile is given by this. Well, in our model, we assumed that we start from here and that we end up at the same height, and this is going to be our max range. So our max range will happen when y is equal to 0. So our max is at y is equal to 0. So let's see if I say 0 here, setting this equal to 0, and then I solve for my x. I'm going to get the tangent of theta times x minus g over 2 times v naught squared times the cosine squared of theta times x squared. So now, okay, if I factor out an x, I'm going to get the tangent of x minus g over 2 v naught squared cosine squared of theta times x here. And so I get two solutions. Either x is equal to 0, which makes sense. They're saying y is going to be 0 and x is equal to 0, but it's also going to be 0 right here. And that's what we're interested in. So then, if that has to be equal to 0, we're going to have tangent of theta minus g over 2 v naught squared cosine squared of theta times x equals 0. Now if I add this term to both sides, what I get is this. And now if I divide both sides by 2 v naught squared cosine squared of theta over g, 2 v naught squared cosine squared of theta over g, then what we're going to get is that this cancels out with this cancels out with this, and we're left with, well, tangent of theta, remember I can rewrite it as sine theta over cosine of theta. So I can say that my x, if I flip this equality, is equal to 2 v naught squared sine theta cosine theta, all of that divided by g. And this is my x max, which I can say this is my range. Now this I can rewrite using a trigonometric identity into 2 v naught squared times the sine of 2 theta divided by g. And now the thing is that we're getting this top one, but sorry, made a little mistake here. This 2 is part of this equality, so it's not going to be over here. Now we get the same expression as the one that we have there. So this is our other solution. Well, now they ask us, show that the maximum height of the projectile is given by h. Well, if I take my y, let's take my y right here. Copy, and I want to find the max y. So this is going to be part D. I'm going to paste it over here. I'm going to bring it down a little bit. And I'm going to take away that box. Now, I'm going to say this is part D. If I take the derivative of this, what do I get here? Well, the derivative of each term, remember that the x is the only non-constant here. So I get tangent of theta minus 2g over 2v naught squared cosine squared of theta times x. Because basically I subtracted one from the exponent and then I multiplied by the original exponent. So using the power rule. So this goes away. And now I can say, I can find my x when the derivative of that is equal to 0, which is going to give me the x at which y is at a max. So doing this seems similar to what we were doing over here. It's just that we don't have a 2 now. So really now if we solve, what are we going to get? Well, we're going to get tangent of theta is equal to g over v naught squared times the cosine squared of theta times x. Now I can rewrite this tangent of theta into sine of theta over cosine of theta, for which I can simplify these by multiplying both sides by cosine of theta. And then if I multiply both sides by v squared cosine theta, I get v naught squared sine of theta cosine of theta, and I divide by g is equal to my x. Well, now I could take this and put it back into my original y function to get what y should be. So let me just do that real quick, and let me use this arrow. So now we're going to go here, and we're going to be saying that y is equal to the tangent of theta times x at which y is max, which is v naught squared sine of theta cosine of theta, all of that divided by g, and minus g times whatever I wrote in that parenthesis, but now it's squared. Sine theta cosine theta, all of it divided by g, and all of it squared. So what do we get here? All right. And I forgot to put right here that we also get all of these terms which were the coefficients of the x squared. Okay, so now let's take this and let's break it into sine theta, cosine theta, so that when we multiply these things out, one of the cosines cancel out, and here we get v naught squared sine squared of theta over g. Okay, now let's try to do something similar here. Well, we got the g, we'll simplify with g squared. So I can, in fact, rewrite this as squared, squared, squared. That's going to be to the fourth. And now we can just simplify here. This is going to simplify with this. This is going to become a 2. And so here we're going to have minus sine squared of theta v naught squared divided by 2g. Okay? And now that we have this, what do? Well, let's take a common denominator. So let's multiply this by 2 so that we have this. And now we get what? Well, now we get that 2 of something minus 1 of that something, where this is 1, is equal 1 of that something, which is going to be sine squared of theta. And then this is all going to be divided by 2g. And this is going to be our y max. And we got the same thing. So this is our answer right here. Well, guys, I hope this was a useful detour into projectile motion. And I will see you next time.